Thank you. Wow, thank you for this nice introduction. Do you agree to give failure a chance? I know most of you would say, can you not? But you know, failure will still exist, whether we give them a chance or not. And the best way to have resilient applications is that despite the existence of failures, our systems will keep running. And having distributed systems with services that interact with each other, it's very easy to have failures, and failures are inevitable in this environment, especially if we have this system depends to the network and external services. For sure, we can have some failures that even temporary failures, if there is a new deployment happening or there is some network issues that is just temporary, but sometimes it can affect our other services. Imagine one failure in a service will make another service fail, and you think that you have 5 services are running in your production environment, and suddenly you didn't notice, maybe a customer will just complain, and then you find out none of your services is running just because one failure happened in one service, and this is really bad. So we have to make sure that we build resilient applications, and for this we need to have a resilient architecture which starts from the infrastructure layer. We can have, for example, some copies of our resources and our services, like different instances. In case one of the instances went down, the service will rely, the other services will rely on the other instances. And in case if, for example, if we have we are using AWS services and one of the region went down, we can rely on other region in this case. And if we have elasticity in our resources, in case if one of our services needs more resources, they can auto-scale automatically in this case. And it's very helpful for developers and the whole team, engineering team, to have infrastructure as code, to have a repository that you can get back to it to see each service, which kind of resources it uses in the infrastructure. You can maintain it. Whenever you add a new service, you can see in your in GitHub, you can see the history. And even sometimes I like that in Life Intent we are using Terraform, DevOps maintaining this project, but sometimes we can also set up our new services or maintain some services there, so we will have more knowledge. Not only the DevOps team would take care of this, so it's very helpful. And in this presentation, I'm going to focus more on the application design. And these are there are more requirements for this, but it's very important to think which programming language is better to use that will prevent you to have unnecessary errors. If you choose a statically typed language, you will prevent programmatic bugs that are unnecessary. And if you use immutable data types, it will also prevent some problems of consistency, and also it will help you to test your programs, to have, to also be able to reason about your program using types. And for this, we can use Scala as a language, but Scala is flexible. We can also have mutability on it. So this is why we need a functional Scala, a functional programming library that works well with Scala, and also that helps us to manage errors using composability and the benefits of functional programming. And there are many functional Scala libraries that we can use, and here I'm going to use ZIO. ZIO has a very strong data types that helps us to capture errors, and we will see how we can manage errors on ZIO. And also, to build resilient applications, it's necessary to have like some recovery mechanisms and to use resiliency patterns. And for this, there are different libraries. There is like Java library resilience 4G. There are like some other, for example, if we want to use HTTP clients, in our case, in Life Intent, we use software mill STTP that under the hood uses some resilience pattern, which is a circuit breaker pattern that under the hood uses resilience 4G. In this presentation, I'm going to use resilience. I took the chance, there is a resilience library. I got the chance in order to prepare this presentation to also learn about it. Also, besides having a resilient application, it's very important for us to expect the unexpected as a programmer. We should be curious. We think like, okay, if in this scenario, we think about different scenarios. If what will happen in this and that, and how we should prevent this problem to happen, etc. And we should also have some tools to monitor and debug our programs and test. And ZIO will help us to do that because it has different data types and features that will help us to monitor and debug and test. And we should be patient because I know it's frustrating to have bugs, and sometimes like you don't expect that this kind of a program that might fail with something that you even didn't know about, that a failure that exists. And failure is a learning experience. And it's an opportunity also, whenever you will see the next time this error, you can also mentor your colleagues and tell them about your experience that you faced, that when you wrote this code in that way, it failed in this way, etc. And like implicitly, you will find yourself, you become resilient. And during this process, it's not easy. You need to find a cope mechanism, maybe a crying room or like a boxing or something, and then keep going, never give up. Personally, I really liked this one. There is like this button, it makes noise. Like I write code and then continue. I know it's very frustrating. Now, let's see how we manage errors using ZIO. This is like in a smaller scope because like we want to have resilience in our distributed systems, but it's necessary that our services are well implemented, like having a good, using a good libraries that really help us to handle errors, etc. So let's see how we can do that with ZIO. Whenever we describe our programs in ZIO, it's an immutable data type. Like when you describe, usually when we write programs, simple programs, it directly interact with, like for example, just a simple program to print out a message, directly it will print out a message. But with ZIO, it will do nothing. It just describes that I want to create a message, and you decide if you want to run it, or if you want to run it with a testable environment, or something like this. And you have control over your effects. This is why we call them functional effects. And if you have this description, like this type is called ZIO. It has 3 type parameters. And just by looking to this type, you understand this program requires these dependencies. It might fail with expected errors of type E or succeed with A. And because we are going to focus on errors, like, okay, like after we try to run our program, we are going to have this, under the hood, there is a runtime system of Zio. It will translate the Zio type into exit of EA, and we are going to focus on the failure part. On the failure part, this type will help us to understand what happens. And it has cause. This helps us to, because it will capture all the cause that, of your failures in the program. So the cause can be because of expected errors, or because there is unexpected error. There is like your program dies because like, it throws an exception that you didn't consider to handle, or because of the program has been interrupted. And sometimes we have parallel programs running. Also, you can capture this because cause has other data. It's a data structure because it has like both subtypes that will capture the left-hand side. It's like a tree, binary tree. It will capture the cause of this program on the left hand and in the right hand. And also there is then, in case, for example, if you have a program that you handled its error, and the program that you use it to handle this error also failed, so it will be described in then data type. So this is why Zio is a good library to use for, to be able to really debug your errors. You can customize your expected errors with map error, for example. You can check out, you can like define your error type for your applications, and you can handle all types of errors by using catch-all or folding and handling your errors. Or you can have like, for example, a fallback program. In case this program fails, or else do this, run this. And you can also expose all the causes using sandbox, for example. You can also convert your unexpected errors into errors. I mean, like when you use unrefine, for example, and you have some expected errors, and there is something happened that you didn't expect that will throw an exception, and it will cause the program to die. If you want to handle all the possible errors, you can use unrefine and transform the unexpected errors into customized errors. Also, you can pick at errors by using tap error or tap error cause. So you can here, for example, in case if you want to log your errors or you want to add some metrics, you can use that. And you can retry in case of failures. So all of these features in Zio, there are more than that. So this is the reason why it would be a good choice. Now, let's see the resilience patterns in a larger scope. Resilience patterns will prevent our system to have cascading failures. And your system will keep running despite the failure of one of your services. And this, like, the failures becomes a natural event that doesn't affect your program from running. There are some common resilience patterns that I'm going to explain in this presentation. Rate limiter, bulkhead, timeout, retry, and circuit breaker using rezilience, which supports Zio. It uses Zio under the hood, and it helps us to use these patterns. And I'm using this version that supports Zio 2. Now, let's see an example. I actually choose a pizza restaurant application because I know you are hungry, so maybe I will inspire you to. We have menu management that like the restaurant will manage by changing the prices and the items, and the order will validate if the customer ordered this item that it still exists there, etc. These services are interacting with each other, and when a hungry customer orders a pizza, and if everything went well during the payment and the order is validated, it will be sent to the restaurant. And once the pizza is ready, it will be delivered to the customer, and the customer will be happy and eat their pizza. So this is the happy scenario. Now, let's talk about problems. This restaurant has limited resources. It has limited ovens. They cannot, they have amount of numbers of pizza that can be done at the same time, and limited labor force and cars. So to avoid having cold pizza, angry customers, exhausted chefs, and like no cars, so this will cause the cold pizza. So to prevent this, we need to find a way to reduce the traffic and reduce the consumption of the resources and use them only when there is capacity to process them. And this, we need a proactive solution to prevent the situation to become a problem. And rate limiter can help us to solve this. It will limit the rate of the request, the number of the requests per an amount of duration of time. For example, we want to have, let's say, 5 pizza per 10 minutes. We can use rate limiter for this in our services. And here, just by, this is using rezilience, we can call rate limiter and make this type using the configuration, and then we apply this pattern into our program. And this, under the hood, it will put the requests, it will wait in a queue, it will wait, and then they will be processed at this interval of time. And then, like, this amount of requests will be processed, and then the next ones will be processed all together, and then like this. So we solve this problem with this pattern. Now let's see another problem that could happen if we have many concurrent requests that will cause resources to be exhausted, and this might also cause failures to be cascaded. So to see it closer, let's try to think about this scenario. Let's say we have 5 requests, concurrent requests, that are sent to order, and the order checks if the item is still valid. 4 requests succeeds, but the latest one caused resource exhaustion in the menu management, which was cascaded to order. But it's okay, 4 concurrent requests succeeded at least, so they will pay their order. And during payment, we want to validate to the order to send it to a restaurant, but the order service is down. And now, payment will return an error to the customer after they paid. I really hope that they got refund. But imagine this scenario. So let's see how we can solve it. We can isolate elements of the service by features. For example, in order service, we can have like menu management running, like we can see them in a thread pool way. We have menu management separated, the restaurant notifier feature separated, the order controller that will validate, that will interact with payment to validate the order, and the delivery notifier. We separate our features like that. And also we need to avoid resource exhaustion, so we limit the concurrent calls that we accept. Otherwise, if it will be exhausted, the whole service will be affected. So let's see how this will happen in our, when we send an order. So this, when the latest request will fail, like previously we saw, when it will fail, it will, and the payment will validate the 4 that succeeded, it will work because only the payment, only the menu management was failing. So this helped us to solve this problem, and this pattern will also prevent the problem from happening, and it is a proactive solution which call it Bulkhead. And it limits the number of concurrent calls, and under the hood, like whenever we define Bulkhead, it will create, it's like running in different, it will fork the different fibers will be running. So this will not affect the other features from cascading the failure. And we can configure this by specifying the maximum amount of concurrent calls and the maximum queuing. Because if, for example, we want to accept 5 calls, and then there are, like, let's say 6, we enqueue, it's okay, we enqueue this request, and it will wait until the other, when there is a space, the other request will be processed. But if the maximum number of Q1 exceeds, it will return bulkhead rejection error. It's better than exhausting the resource. This will prevent us from that, because in this case, it means there is something wrong in our system. If there is we wanted to process and the max queuing exceeds. And this is how we use rezilience to build Bulkhead and configure it in this way. And we apply it to our programs that way. Let's say we apply it in our HTTP clients, and we pass this Bulkhead, and we apply it in that way. Cool. Now we solved this problem. Now, let's say if the customer, after they paid, they ordered the pizza, they got a call, and the payment was waiting, it's using unnecessary resources. We can interrupt this if it exceeds a timeout duration to prevent any, why we have to just keep these requests that take too long. So it's better to react into this problem whenever there is a timeout, it just fails with timeout. This will prevent us also from using unnecessary resources. And it's simple to configure timeout, and also in Zio we can use timeout in our program. And in case if the timeout exceeds here in the rezilience library, it will return call timeout, and here how we use and we configure the timeout, and we apply the timeout into our programs. Cool. Now let's go back to the transient failures that could happen. This could happen for a short amount of time. It's temporary errors. We just need to try again. So for this, we can use retry strategy that will retry the programs on failure. And in rezilience, by default, it uses exponential backoff. You can specify the minimum, maximum, and factor. And you can also use this data type using the schedule, Zio schedule and you specify which conditions you want to retry, for example, for a given type of errors or how many times, etc. And this is how we build our retry policy, and then we apply to our programs using apply method. Cool. But imagine if we have failures that will take long to recover. Let's say the restaurant forgot to pay the electricity. There is no oven working. There is no internet. So it wouldn't be cool when we send a lot of orders and we will not process these orders and the customer will be waiting. So we shouldn't retry in this case because we might exhaust the resources without solving the issue. There is this pattern called circuit breaker. This prevents the failures from cascading by giving the failure service time to heal. And in this pattern, it stops the traffic once failures reach a certain threshold. We can configure a threshold, let's say an amount of failures. If, for example, the system fails 3 times, succeeding, like next to each others, it will directly stop communicating with the failed service. We will see it in detail. There are 3 states for the circuit breaker. Closed, this is the initial state when the calls succeed or fail within a threshold. And open, in this state, all calls will fail immediately without interacting with the service in question. And half open, this will, after an amount of time, the opened circuit breaker will become half open and checks if the service went up again, it will go back to the closed state. Otherwise, the breaker will go to open state again. We will see this more detail. And here how we can configure the circuit breaker by tripping strategy, and we can customize this. There is also, like we can, for example, by failure count or failure rate. And there is also, we can define our reset policy. And this is when, for example, after the circuit becomes open, it will wait an amount of time to be to half open state. Let's see this by example. When we apply circuit breaker pattern into restaurant service, the calls will go through circuit breaker, doesn't go directly to the restaurant. So let's say we have failure count, the threshold is 3. And the reset timeout, 1 minute, and using exponential back-off strategy. In the beginning, the state is closed, and there is a request sent to the restaurant. It will go through the circuit breaker, and then the restaurant, when the restaurant succeeds, the call succeeds, it will return the result. Now, let's say the restaurant, the call failed. When it fails, the failed calls will be incremented, and the next call, let's say it succeeded. When it succeeded, the failed calls will decremented because we want to count, because the circuit breaker will monitor how many calls will fail, but one after the next. So we will know, this is the way how the circuit breaker knows that this service really needs time to recover. So now the failed calls are 0, and then again, when it fails, it counts increment to 1. It fails again, it will be incremented to 2, and now it is the failed calls are equals to the threshold. In this case, the state will become open. Now, whenever we receive requests towards restaurant, the circuit breaker will not call restaurant. It will fail directly with circuit breaker open error. And 1 minute later, because to remember, reset timeout is 1 minute. So now, whenever we receive, the order calls the restaurant service, it will always fail until 1 minute. 1 minute later, the state becomes half open. Now, when we receive a request, the circuit breaker will try. If the restaurant will return failure, the circuit breaker will be open again. And then it will fail again and again without calling a restaurant service, without overloading the restaurant with many requests, and until 2 minutes, because now we are using exponential back-off strategy with, let's say, factor 2, and I think maybe 4 it should be. Okay, a few moments later, the circuit breaker go back from open to half open. And whenever we receive now a call, just this time, after becoming half open, the circuit breaker will try to call restaurant, and if it succeeds, it will return okay, and the failed counts will go back to 0, and the same process go over and over again. And this is how we can use rezilience library. And we can specify the tripping strategy, and here as the example it uses failure count. We specify the maximum failure, and reset policy by default it's using exponential back-off, and we can also specify which failures we can consider as failures. If we want, because sometimes we don't need to do this for example, if there is a bad request or something like this, if this isn't like failures, the communication failures, for example, can be considered as failures. And on state change, you can specify what you want to do. For example, you want to log the state when it changes. And here, how we can apply the circuit breaker just by wrapping our program. Cool. Now we solved our problem. Whenever the restaurant has some issues or something, we will inform the customers to just either wait a bit or try something else. It's better than give them hope without anything. Cool. There is other things that we can do using rezilience library, that we can combine policies. We can have we can call policy.common, or we can also make each patterns, we can call .to policy also. This will transform this type to policies and combine them all together, and then we apply all the policies into our programs. Also, we can integrate rezilience with ZIO config by using this module, and we can call from config and put the ZIO configuration there. Now, what's next? We can use, after we make sure that we have resilient architecture, we are very good, we can use tools for creating chaos to establish confidence in the systems. We can make sure that really that our systems are resilient by, for example, tearing down some pods, or stopping some services and check if it's still working or not. And there are some tools like Chaos Monkey by Netflix. I personally didn't try it. It's scary if I would Like imagine to try to do chaos, try to make sure that there is something wrong in the infrastructure by doing these things in production to make sure that your system is resilient. It's scary, I wouldn't do that. But there are chaos engineering can do that. Yes, they know what they can do. And here, if you are interested to give it a try for a resilience, here is the resilience repository link and Zio. And that's it. Life and Land is hiring, and if you... Thank you. If you are interested to work with us, come and talk to me or my colleagues. We are hiring. Thank you.